Hello, folks. Section 6.1 we've actually already covered a little bit last semester, but I wanted to touch base with it again and really kind of hone in on the relationship between radians and degrees. We kind of mindlessly just did some conversions and some formulas really quick before our semester exam. So now that we're fully getting into chapter 6, I want to make sure that we really understand the relationship between them and how to use them and where they're useful. So the first thing I want to do is take a look at your unit circle here, and I want to go through and put all of our degrees. So we know that starting in an angle in standard position here over to the right side is 0 degrees, but it is also 360 degrees after a full revolution. And we know that we work or we rotate counterclockwise. So I kind of recommend doing the 4 corners first. If you have a hard time just kind of rattling off the degrees all in a row, just do the obvious ones first. So obviously this one's 90 degrees. Then another 90 degrees is going to be 180, and then another 90 degrees is 270, and then I already marked 360 there. And then halfway between all these 90-degree angles is 45 degrees. So there's our 45-degree angle. The 45-degree angle cut here is 90 plus 45, which is 135. Then take 180 plus 45, and you get 225. And then 270 plus 45, and you get 315. And then again, you're back to 360. So they're all the 45-degree cuts. And then all of the others are 30 and 60 degrees. So if this one's 30, then you add another 30 degrees and then you get 60. And then when you add 30, you get to 90. And then when you add 30, you get to 120. Plus 30 is 150. Plus 30, we already have, is 180. Plus 30 is 210. Plus 30 is 240. And then plus 30 is 270. Plus another 30 is 300. Plus another 30 is 330. And then again, we're to 360. So that's kind of how you can easily derive all of the angles if you can't just rattle them off all one after another. So the next thing that we need to remember is that I'm actually going to write it over here, and you'll see why later. But I'm going to write down that, I'll just write up here. There are pi radians is equal to 180 degrees. That was our big find the first time that we talked about this. So what I want to do next is go through the unit circle, and this time I want to write all of the radian measures that equate to the degrees that we already have written. So we could start off our circle at 0 radians, and then half of the circle, 180 degrees, is pi. A full revolution is 2 pi, so that gets us back here. Okay, so this one, if you're good at fractions, then it should be pretty easy for you, because all we need to do is take the semicircle of the first and the second quadrant and divvy it up into further fractions. So like half of the top semicircle is literally pi over 2. So that's 90 degrees. And then you add another pi over 2, and that's where we get pi. And then you add another pi over 2, and you get 3 pi over 2. So those are all of the pi over 2s. Then, just like we did the 45 degrees next, I'll do those, but for radians. So notice, again, if you just focus on, like, if you kind of have this line in your brain and think, okay, well, that top semicircle is 1 pi divided into fourths, this is pi over 4. Pi over 2 is 2 pi over 4. And then this 45, the other 45-degree angle is 3 pi over 4. And then that cuts it literally into fourths. So let me highlight that one there. So this one's a fourth, this one's a fourth, and this one's a fourth. So you see how it's evenly divided. And then you do the same thing to the third and the fourth quadrant. So you keep adding more fourths, right? So if you have 4 fourths, you add another fourth, then you're at 5 fourths for this one. And then you're at 6 fourths, which is already 3 pi over 2. And then you're at 7 fourths to get the next one. So all of these are just adding 1/4 to those pi pieces. And you do the same thing for thirds, if you want, or you could do the 30 degrees, but the thirds to me, well, let's do 30 degrees. Those are by sixths. So this is pi over 6. There's 1 pi over 6. So it's 1/6 of the pi. Let's do that in like gray. So this little gray piece right here, that's 1/6. So if I do the next one, that's 2/6, which is the same thing as 1/3, right? It reduces. So this one's going to be pi over 3. Then add, so there's the second sixth. Then we have the third sixth, which 3 over 6 is pi over 2, which is already there. Then you have 4, the fourth pi piece. And 4 over 6 is the same thing as 2/3. So this one is 2 pi over 3. And then you have 5/6. So 5 pi over 6. And then 6 over 6 pi is the same thing as 1 pi. It reduces. And then you do the same thing again for the third and the fourth quadrants. You just keep on adding sixths. So if this is technically 6 over 6 pi, then add one more, and that's 7 pi over 6. Then add another one, and that's 8 pi over 6, but 8 pi over 6 is the same thing as 4 pi over 3. Add another sixth, and that's going to be 9 pi over 6, which is 3/2. Add another one, and you get 10 pi over 6, which is 5 pi over 3. Then another one, you get 11 pi over 6. Okay, so that fills out. So if we did all the conversions, so remember we talked about how to convert from degrees to radians and radians to degrees. So let's recap that really quickly. If I want to convert, I'll write it up here at the top. If I want to convert from radians to degrees, then I simply multiply the radian that I have by 180 over pi. And that will get me from the radian to the degree. So like here, if I wanted pi over 2 as a degree, I'd do pi over 2 times 180 over pi, and then I get 90. If I want to go from degree to radian, then I multiply by pi over 180. And so typically, and I discussed this last time, radians are associated with pi. Not all of the time. Sometimes I can talk about radians and say, oh, it's about 5.2 radians. But typically our radian measurements, especially associated with the unit circle, will have pi with it. So that'll kind of help you figure out, should you be multiplying by 180 over pi or pi over 180. Now, we used the unit circle before, and I always talk about how if you know the first quadrant, if you know the coordinates of the first quadrant, that is enough. And this is where, when we did our unit circle with the bow ties way back before Thanksgiving break, that's kind of where this comes into play, right? We had basically at this 0 degree here, this was the coordinate 1, 0. And so all the 4 corners have, we deem the radius of the circle to be 1. So it goes out to 1, and then it doesn't go up or down at all. On the y-axis, this is opposite. This one is 0, 1, that coordinate point here. So again, we're talking about the coordinate points on the circle. Halfway between this revolution, and again, this has to deal with our 30, 60, 90, and 45, 45, 90 triangles. If I were to do my 45, 45, 90 degree triangle and take the tangent of those ratios to get my hypotenuse, then the coordinates at pi over 4, 45 degrees, are square root of 2 over 2, square root of 2 over 2. So that one is the same. And that should make sense because Remember, tangent is y over x, and if these have the same y and x value, then the tangent is 1, which is the slope of 1. So it's saying that the slope of this guy right here goes through the origin is 1. And then the other two, basically, if you kind of imagine this point here at 30 degrees goes the furthest on the x-axis out before it goes up, and the bigger of our numbers is the square root of 3 over 2, and then it goes up 1/2. And then 60 degrees is opposite. It goes to the right 1/2, and then it goes up square root of 3 over 2. If you can generate those coordinates, particularly just those three there, the three weird ones at 30, 45, and 60, then all of the other three, imagine if you reflected them over the axes, that's where the other bow ties come from, right? So, for instance, if I take this 30-degree angle and I reflect it, oh, interesting, reflect it over the y-axis, I get this one. So that's why when I reflect it, I get the same exact coordinates, except in the second quadrant, I have a negative x value and a positive y value. So these are going to be the same three coordinates. I don't really have room in it. It's okay, we don't have to write them all, but the signs are going to be negative, positive. In the third quadrant, if I took that 150-degree angle, which has the same coordinates as the 30-degree angle, and I reflected it over the x-axis, then I end up with this one here. So again, the same coordinates, but these will have negative, negative signs. And then if I reflect that over the y-axis again, I would get this one at 330 degrees, which will have the same two numbers here, except it will have, the first one will be positive, the second one will be negative. So that's a brief recap of what we learned in chapter 5. Now, we also talked about how do you find that? So, if I randomly ask you, okay, guys, what is the sine of 300 degrees? And if you don't have time to draw out the full triangle, the first thing you want to figure out is, at this 300-degree angle right here, what is its reference angle in the first quadrant? Well, visually, you can see where this one will reflect to equal, and then you can kind of do that. But in the heat of a moment or on a test when you can't generate the whole circle, we had this little chart that helped us figure out how to find reference angles. And basically it was this: if an angle is in the first quadrant, then it is its own reference angle. We just call it alpha. If an angle is in the second quadrant, to find the reference angle, you do 180 minus alpha. In the third quadrant, we did alpha minus 180. And then the fourth quadrant, we did 360 degrees minus alpha. So I'm going to hop around here for a second. We're going to come back to how to find a reference angle in radians, and I want to answer number 1. So we've already done questions like this, but just to kind of bring it back to the forefront of our brains, if I ask you to evaluate the cosine of 480 degrees, the first thing to know is that I want this as an exact answer, not as, a rounded decimal. Some of you guys would just plug it in your calculator, give me the decimal, and cross your fingers that that was good enough. That's too easy, obviously. The point is I want something exact. So first thing to remember is that the cosine is the the x coordinate. I'm looking at a different problem on my paper. Okay, sorry. Cosine is indeed the x coordinate. So I need to figure out, where does 480 degrees lie on my circle, and what is the x coordinate at that point? And basically this can kind of be broken down into 4 steps, okay? The first step, I'm going to just call step A, is to figure out, where is this on the circle? Okay, now 480 degrees as is not on the circle. Our circle goes up to 360. So the first thing we want to do is find a coterminal angle. Find a coterminal angle actually on the unit circle. So remember, coterminal means like 0 and 360 degrees are coterminal. If I add another 360, I get 720. 720 is coterminal with 0 and 360. So it's just adding on revolutions and landing on the same spot over and over. So I want to figure out what coterminal angle is actually on the unit circle. In other words, that's going to be between 0 and 360 degrees. In order to find that, all I need to do is take 480 minus 360, and then I get 120. And 120 is on the unit circle, so we're in business. Now, it's not in the first quadrant. So the second thing, or part B, what we need to do is we need to find the reference angle. So if you refer back to our chart up here, 120, as I mentioned, is in the second quadrant. So in order for me to find the reference angle, I'm going to do 180 minus alpha, or in this case, 180 minus 120, and then I get 60 degrees. Part C is, okay, well, what are my coordinates that I'm dealing with now? Well, at 60 degrees, and this is where, again, if you can generate the first quadrant, you're in business. So at 60 degrees, we're dealing with those coordinates there, 1/2 comma square root of 3 over 2. So the only difference between the 60-degree angle and the 120-degree angle is that since 120 degrees is in the second quadrant, the numbers in the second quadrant have signs negative, positive, right? So this is going to have a negative 1/2 positive square root of 3 over 2. So what this means, and essentially just your last step, is you're going to take your, remember that 120 is coterminal with 480. So if I know that 120 degrees has these coordinates, then that must also imply that 480 degrees has the same coordinates because those are coterminal. So it has the same as the 120 degrees, and therefore that implies that the cosine of 480 degrees, cosine is the x value, so the x value of that coordinate is just negative 1/2. Now in this case, if you plug that into your calculator and got a decimal, you'd actually get lucky because it is just negative 0.5. So you can do that to check. You just need to make sure, because you're typing in a degree, if you're going to check in your calculator, you want your calculator to be in degree mode. Okay, let's change gears and let's talk about radians. If you look at number 2, I'm asking you to evaluate the sine of 7 pi over 6. Previously, I basically just kind of led you to go ahead and convert 7 pi over 6 to degrees and then follow the steps as we did in number 1 to find, the value. But we're going to need to get really good at using radians, so we're going to do the same steps, but with a radian mindset. So we're going to follow the same things. So part A, we first need to determine where is 7 pi over 6. Is 7 pi over 6 on our circle? So if you look at it, it is. It is right here. So part A is actually done. You don't need to find it. Part A, or 7 pi over 6 is on the circle. So you're good to go. Part B is it in the first quadrant? And if not, you need to find the reference angle. Well, we just saw up above, it is not in the first quadrant, it is in the third. So we need to go ahead and find the reference angle. Now, to find a reference angle, you're going to do something similar to our little chart. Oops. Something similar to our little chart here, except you need to remember that radians and degrees function very differently. So if you keep this in mind, that 180 degrees is the same thing as pi, then we're basically going to be computing the same, except instead of using alpha, I'm going to use theta. So if an angle theta is in the first quadrant, it's its own reference angle. If it's in the second quadrant, you're going to take pi minus theta to get the reference angle. In the third quadrant, theta minus pi. And in the fourth quadrant, instead of 360 minus, in this case, a theta, we're going to have 2 pi minus theta. So that's how you find reference angles using radians. So we're in the third quadrant over here with 7 pi over 6, meaning we need to do theta minus pi. Theta minus pi. So I'm going to do 7 pi over 6 minus pi. Now, in this case, guys, pi is going to be treated like a variable. So don't actually type 7 pi over 6 minus pi in your calculator, because you're going to get all kind of crazy decimal stuff, and it's not going to be exactly what you want. If you treat it as a decimal, essentially what you're subtracting is just 7 sixths minus 1. Okay? By hand, I need common denominators to subtract these. So that's going to be 7 pi over 6 minus, if I want this to have a denominator of 6 as well, I can't just divide it by 6. I need to multiply it by a version of 1. So 6 over 6 is the same thing as 1. 7 pi over 6 minus 6 pi over 6 is 1 pi, or just pi over 6. Okay, so again, you kind of treat pi like a variable by just subtracting the numbers out front. 7 sixths minus 6 sixths equals 1 sixth, and then tack on pi. If you have the aid of a calculator, you could simply, in your calculator, just do 7 over 6 minus 1, and then whenever you get to the decimal, just hit math, enter, enter, convert it back to your fraction. Your fraction should equal 1 sixth, and just remember that it's actually 1 pi over 6. And if you type this into your calculator as is, you would get the decimal the same as if you just divide pi over 6. Okay, so what does this mean? Step C is, okay, what are the coordinates? So the coordinates of pi over 6 are, looking at my unit circle here, and again, this is where you need to be familiar with how your radians match up to the degrees. Where is there it is. Okay, at pi over 6, I'm using these coordinates here. Square root of 3 over 2, comma 1/2. Square root of 3 over 2, comma 1/2. Now, the angle was not pi over 6. Pi over 6 was the reference angle. The angle was 7 pi over 6. So the only difference between these two angles is that 7 pi over 6 is in the third quadrant. In the third quadrant, our coordinates are negative, negative. So we're going to have negative square root of 3 over 2, negative 1/2. So then that leads us to finding our answer. The question was, what is the sine of 7 pi over 6? Well, the sine is dealing with, we didn't talk about this earlier, review this earlier. Sine is dealing with the y coordinate. The y coordinates at 7 pi over 6 is negative 1/2, getting that from the coordinate here. And again, if you put that in your calculator to check your answer, you would get lucky by not having a decimal to deal with. You get negative 0.5. The only difference is if you type in sine of 7 pi over 6, you need to make sure your calculator is in radian mode. So you might be switching modes back and forth if you're going to check stuff in your calculator. Let's do another one. Evaluate the tangent of 14 pi over 3. So let's follow our steps. Step A was, is 14 pi over 3 on the unit circle? The answer is no. It's a lot bigger. Okay, there is no 14 pi over 3. So what you want to do is you first need to find a coterminal angle with 14 pi over 3. Now, revolutions and degrees, or you just keep adding or subtracting off 360 till you get a coterminal angle. With radians, you're going to add or subtract off 2 pi to find your coterminal angle. Okay, so let's do that. So if I do 14 pi over 3, and I want to subtract off 2 pi and see, do I get an angle on the circle? In order to do that, I need to have common denominators. So if this one's going to have a denominator of 3, I'm going to multiply it by 3 over 3, which is going to be 6 pi over 3, right? Because 6 over 3 reduces back to 2. And again, treat pi like a variable. So just subtract the numbers out front. 14 over 3 minus 6 over 3 is the same thing as 8 pi over 3. 8 pi over 3. Go back up and look at your unit circle. Unfortunately, 8 pi over 3 is also not on the circle. So you need to do it again. You need to subtract again. So if I subtract 8 pi over 3 minus 2 pi, again, that means I'm going to do 8 pi over 3 minus This one I'm going to do times 3 over 3, so it's going to be 6 pi over 3. 8/3 minus 6/3 is 2/3. So 2 pi over 3. Again, if you have the aid of a calculator, you could have just done 8/3 minus 2. Make sure to put this in parentheses, and then hit math and enter, get your fraction, and it should give you 2/3, but you have to remember that it's actually 2 pi over 3. So there's our coterminal angle is 2/3. Go back and look at your circle. 2/3 pi is not in quadrant 1. It's in quadrant 2. So we need to second find a reference angle. So part B, to find a reference angle for 2 pi over 3. In quadrant 2, using our little chart here, if I'm going to find a reference angle, I'm going to do pi minus theta. Pi minus theta. So pi minus 2 pi over 3. If I want to subtract this, I need to have common denominators. So if I multiply this first pi by 3 over 3, then I get 3 pi over 3 minus 2 pi over 3, which is 1 pi over 3, or just pi over 3. Part C is, okay, what are the coordinates? The coordinates at pi over 3, using your unit circle, hopefully you're able to generate that, are these that we've used earlier, 1/2 comma square root of 3 over 2. 1/2 square root of 3 over 2, but that's not our angle. Our angle is in the second quadrant, which is 2 pi over 3, so that implies that our angle has negative 1/2 square root of 3 over 2 as its coordinates. Okay, so then the last part, part D, is to actually evaluate the original question. The tangent of 2 pi over 3 is the same thing as the tangent of 14 pi over 3, because these angles are coterminal with each other. That was the very first thing that we found. Now, tangent is found by comparing y over x. So our y coordinate is the square root of 3 over 2. Over the x coordinate is negative 1/2. Now, stacked fractions are not considered reduced, so you need to do some work. Square root of 3 over 2. Dividing by a fraction is the same thing as a multiplying by the reciprocal. So if we multiply by the reciprocal of negative 1/2, we get negative 2 over 1. And then if we multiply straight across, we get negative 2 square roots of 3 over 2 times 1 is 2. And then reduce one more time, negative 2 over 2 is negative 1. So then we get negative square roots of 3. Okay, so that's how you evaluate at particular radians. We also talked about arc length and the area of a sector. So just to review those very quickly, those were pretty easy given the formulas. So we had for arc length, we had S equals R times theta. And then for area, we had area equals 1/2 R squared times theta. So to break down the variables here, S stood for arc length. Arc length. R stood for radius. Theta stood for the angle in radians. That is so important that you understand that it is in radians. This equation does not work if your angle is in degrees. Same thing for area. So this is the area of a sector. Equals 1/2. This is radius squared. And again, the theta is angle in radians. So an example using these, number 4, it says an arc is 70.7 meters long. It's intercepted by a central angle of 5 pi over 4 radians. Find the diameter of the circle to the nearest tenth. So the key here is that we're talking about arc length. So that lets me know that we're going to use S equals R times theta. And I'm going to substitute in what I know. I know the arc length is 70.7 is equal to the radius we don't know. So I'm going to leave that as r. And then theta in radians, we know they give us is 5 pi over 4. So if I want to solve for r, it's pretty simple. All I want to do is divide both sides by 5 pi over 4. However, this is where some of you were making mistakes when we did this a couple weeks ago. In your calculator, you have to make sure that 5 pi over 4 is in parentheses when you divide it. Otherwise, your calculator is going to do order of operations. It's going to do 70.7 divided by 5.4 and then divide that by 4. So you needed to divide it by the fraction altogether. If you do that, then you should get that the radius is approximately 18 meters. Recognize that it's asking us for the diameter. So the diameter is just going to be double the radius, which would be about 36 meters. Okay. Number 5, a sector has an area of 15.3 meters squared. Radius of the circle is 3 meters. Determine the measure of the central angle in radians and degrees to the nearest tenth. We're dealing with area of a sector, so area equals 1/2 r squared times theta. So let's plug in what we know. We know the area is 15.3 equals 1/2. We know the radius is 3 squared times theta. So then keep solving. We got 15.3 equals 1/2. 3 squared is 9 times theta. So 15.3 equals 1/2 of 9 is 4.5 times theta. Divide both sides by 4.5. And then you end up with theta is equal or is approximately 3.4. Now you got to remember that theta is the measure in radians. Okay, that's just by default. So this is actually 3.4 radians, and this goes back to what I said earlier, is that not all radians have to have pi in it. Most of them do, but not all need to. So there's your answer in radians. I ask you also for the measure in degrees. So to convert from radians to degrees, we're going to take 3.4. We're going to multiply that by 180 over pi. And technically this is over 1, so if we multiply straight across, you get 3.4 times 180 all over pi, and you should get that that's approximately 194.8 degrees. Okay, so that's a recap of many things that we've already discussed in 6.1, but just to kind of get us back in gear as we look ahead to further sections in this chapter that require a much deeper understanding of radians.